So let's say you want to find the area between two curves. This is a common problem in calculus, and it's actually not that hard. So if we have a graph like this, and we have a blue function, f of x, and a red function, g of x, we're told to find the green area, which is the area under f of x and above g of x. How do we do that? Well, to find the area between two curves, it's just really taking an integral. So the integral is just going to be the integral, so the area between the two curves equals the integral of the top function, f of x, minus the bottom function, which is going to be g of x, and then dx. And then for the limits, we need to find a to b. So a is the leftmost limit, and b is the rightmost limit. So you'll either be told between these two lines, those are your limits, or you can be told just find the area enclosed by the curves, and in that case you have to figure out where the curves meet, and the leftmost intersection is going to be your a value, and your rightmost intersection is going to be your b value. So if you have two curves, f of x and g of x, f of x is above g of x, and you're looking for the area between those two curves, between the intersection points or the given points a and b, your integral is going to be the area equals to the integral from a to b of f of x minus g of x dx. All right, so let's look at this problem. Find the area enclosed by y equals x cubed and y equals the square root of x. So the first thing we need to do is figure out what this function looks like. So to do that, I'm going to say, where are the intersection points? Where does x cubed cross square root of x? So you'll notice that if you set x cubed equal to square root of x, then you'll find that at x equals 0, you get the same thing on both sides. And at x equals 1, you get the same thing on both sides. Now, does this work for any other values? Well, in this case, it won't, because you have square root of x, so you can't have anything less than 0, because less than 0, square root of less than 0 will give you an imaginary number, and there's no way we're going to get an imaginary number on the x cubed. So that basically cuts out anything left of 0. And right of 0, we have 0 and 1, but are there any other values like 2, 3? No. Just x equals 0 and x equals 1. So those are our points of intersection. Points of intersection. And since there's no points of intersection right of x equals 0, that tells us that when we're drawing our graph, we can actually start at x equals 0, and our next important point is going to be x equals 1. So x equals 1. So this is going to be x equals 0 right here. And I'm just going to say each square is 0.25, so 1, 2, 3, 4. X equals 1. And now we're going to draw our graph out. So you'll notice that in the case of x cubed versus the square root of x, since we're at a value of x less than 1, x cubed is actually going to be growing slower than square root of x. So our square root of x will be on the top, and our x cubed will be on the bottom. So now all we need to do is plug this into our integral to solve for the area between those two curves. So we know that a should be equal to the integral from the leftmost intersection. So we'll call that a, to the rightmost intersection, we'll call that b. And we can say that our topmost function is going to be, in this case, square root of x. And our bottommost function, which is what we're going to be subtracting, is going to be x cubed, and then dx. So our area is going to be the integral from 0 to 1 of the square root of x minus x cubed dx. And if we integrate this, then we can say 0 to 1, the antiderivative, so we're going to do x to the 1/2, add a power. So it's going to be x to the 3/2, divide by the new power, so 2/3, and then minus x to the 4th over 4. Let's integrate it so we can cross that out, and we can just do from 0 to 1. And so we can just say, basically we don't need to even use the 0 term because everything's multiplied by x, so we can just say 2/3 times 1 to the 3/2 minus 1/4, 1 to the 4th over 4. In this case, the exponents will just cancel out because they're 1 raised to something. So we can say 2/3 minus 1/4 equals, and that's our answer. So let's just simplify this a little bit. So 2 times 4, that would be 8 over 12. And 3 times 1 minus 3 over 12. So we can say this is equal to 5/12. So our area between the two curves is 5/12. Okay, so what if we have a similar problem where we need to find the area between some curves? But in this case, we're given a graph, and it says find the shaded area A by integrating with respect to y. So the shaded area A is between several curves, actually. So it is between the left curve, x equals cosine y, the right curve, y squared equals x minus 2, this line on the top, which is going to be y equals 2, the line on the bottom, which is going to be equal to y equals negative 2. And as you can see, it actually doesn't have shaded in anything to the left of the y-axis. So we're going to say that the y-axis is another limiting line. So in this case, we're just trying to find the area of the shaded region A by integrating with respect to y. Now, when you're trying to find the area by integrating with respect to y, what you need to notice is that the area A is going to be equal to the integral from the bottom to the top. So they're going to be our limits on our integral. So the integral of the rightmost line, so the right function, minus the left function. And then we're going to integrate with respect to y, so dy. So in this case, we can say that we're going to be integrating a equals to the integral from the bottom to the top of, in this case, our right function is this parabola, y squared equals x minus 2. Now, since we're integrating in terms of y, we need to solve for x. So if we have y squared equals x minus 2, then we can say that y squared plus 2 equals x. So that's going to be our rightmost function, y squared plus 2. Okay? And then our leftmost function, which is what we're going to subtract, is x equals cosine y. So cosine y dy. So we can say that our integral for our area is going to be the integral from the bottom to the top of y squared plus 2 minus cosine y dy. Now, one problem you may notice is if we integrate y squared plus 2 from the bottom, meaning negative 2, to the top 2, then we're going to get these areas to the left of the y-axis, which I'm shading in red right here. We don't want those. So what we need to do actually is take this part, the integral for this part right here, and then we need to take these parts separately and add them. Now, you may think we need to do you may think we need to do 3 integrals, but we really just need to do 2, because these 2 areas are the same, these 2 small top and bottom bits. So let's call this bottom part 1, this middle part 2, and the top part 3. So what we really need to do is notice that A is equal to 2 plus 2 times 1. So we need to find the area of 2 and the area of 1. So the way we're going to do this is we're going to use the same integral, the integral of y squared plus 2 minus cosine of y dy. And now the bottom and top limits are basically going to be where this cosine y function crosses the y-axis. So in this case, we would want x to be equal to 0, and we need to find where y is on that cosine y function. So you should know that cosine crosses the 0 at pi over 2 and negative pi over 2. So cosine of pi over 2 is going to be equal to 0. So we can say that when y equals pi over 2 and negative pi over 2, that x equals cosine y function is going to cross the y-axis. So we're going to say negative pi over 2 to pi over 2 as our limits. And an easier way to do this, actually, is to notice that we have some symmetry there. As you can see, this part is the same as this part. So we can rewrite the integral as 2 times the integral from 0 to pi over 2 of y squared plus 2 minus cosine y dy. And now we need to solve that. So let's just find the antiderivative. Y cubed over 3 plus 2y minus, so we have cosine, derivative of sine is cosine. So that means that the integral of cosine is sine. So we're going to say minus sine y. And we're going to be taking that from 0 to pi over 2. And we've been multiplying that by 2. So what we have here is pi over 2 cubed over 3 plus 2 times pi over 2, so that's just pi, minus sine pi over 2. So the y and the 2y will just cancel out. And so we're going to be subtracting negative sine of 0. So negative minus negative is positive. So plus sine of 0, which is 1. And we're going to be multiplying this whole thing by 2. All right, let's just do this math really quickly. Pi cubed over 8 divided by 3 plus pi minus 0 plus 1. So here we have 2 times pi cubed over 24 plus pi plus 1, which is going to be equal to pi cubed over 12 plus 2 pi plus 2. So that is going to be our middle area. So what we called section 2, this part, is this. So I'm going to write S2, section 2. Now we need to find section 1 and multiply that by 2. So in the case of section 1, we're going to be taking as our rightmost line the parabola, and as our leftmost line x equals 0. So in this case, we're just going to be doing the integral from the bottom, which is negative 2, to the top, which is going to be our intersection point, which is pi over 2, negative pi over 2, of that parabola. So we can say that the area of section 1 is going to be the integral from negative 2 to negative pi over 2 of this parabola, which the function for that is y squared plus 2 dy. This is a pretty trivial integral. Y cubed over 3 plus 2y from negative pi over 2 to negative 2. So we're going to say negative pi over 2 cubed divided by 3 plus 2 times negative pi over 2 And then we're going to do minus -2 cubed over 3 minus 2 times -2. Simplify that down. So simplifying that down, we're just going to get a1 equals to 64 minus pi cubed divided by 24 minus pi plus 2. So we could basically say that our area of the green part is going to be 2 times area 1 plus area 2. And we know our area 1, so we can say that A is equal to 2 times 64 minus pi cubed divided by 24 minus pi plus 2, that plus, and then our area 2, which is going to be pi cubed divided by 12 plus 2 pi plus 2. And so that's basically our shaded green area, our A. So, well, that's pretty much all you need to know about the basics of areas between curves, and I hope this was helpful. All right, have a good one. Bye.